So, good afternoon. Welcome to today's lecture. Uh, Last class we I'd introduced you to the instrument that we can use to measure photosynthetic rates, and also introduce you to the BioCro software, which is the plan model that we'll be using, and how to what are the documentations that where you can access the documentations, and how can you play around with that with some basic functions of BioPro. So again, today's lecture series will also be a continuation of that, as to how we can generate these ACI curves using BioPro, and how FPCB model is applied or is used by BioPro to generate the maximum carboxylation, limited photosynthesis, RUBP regeneration, limited photosynthesis, and TPU rate, limited photosynthesis. So again, I would just like to take you all to so I had said how to and when we are using RStudio, we first so in the beginning, when we open RStudio, say we need to create a new file, we click on this tab and create the new file. We also want to make sure if the file is being saved and is being run in the particular directory or a folder of our choice. So we get the get working directory using the get wd, which means get working directory command, and we check which is the which is the directory that the program is working on right now. So in order to change to the desired location that we require, we'll click on the session tab and then set working directory, choose directory, and choose whichever directory that is of interest to you. So I'm choosing this folder where I'm storing all the BioCro codes for I'll be presenting during this class. So then I set the working directory to this this one. So if you see here, the same thing can be done using this command. There is a command called set working directory. So if you set working directory, and if you know what is the address of the path that you want to put the file into, then you can directly give this address here within double quotes. And if when you press enter, the working directory will be set to this location. Now if we type in get working directory, we'll see that the working directory has been changed to our desired location. In my case, this BioCro code, it's BioCro. That's a typing error. Is my screen visible? Do I have to zoom in or something?
Ma'am, it's fine.
Okay. Let's see. Yeah, this will do. Okay. So last class we checked how to install this. So once this package is installed, it will be available in the in our library, where all different sorts of packages are available. So if we type in library and BioCro, it is going to show over here. This is because this package has already been installed. So you can take it, and like I said, you can either run this line by clicking on this run button over here on the right side, this run button, and then you will see that this library has been loaded within this environment. I'll show an example of what happens if you don't load the library. So now in this file, we have loaded the library. We want to get what all functions are available within this package BioPro. I mean, what all commands are available to apply what are the different kinds of functions available so that we can make use of those commands to apply on data to run simulation. So for that, we will type in ls uh, parenthesis, double quotes, package. What is the package name? And it will be Biocro. And again, enter. So here we are getting around 36 functions which is available within the Biocro package. You can add CSV rows, add time to weather data. Then there is getting all the modules, getting all the ODE solvers, ordinary differential equation solvers, getting all the quantities. Then there are other packages like other functions called run Biocro. This function is used for running the model for the entire plant. Then there is getting module information, making a response curve. So many such functions are available, already built-in functions, and using these built-in functions, we can apply it on whatever data we have to generate curves or to get the results of certain processes, etc. Now, what happens if we don't load the library is, now say I'm closing this. So I reopened this one, and I'm just going to start with trying to see if this the package is already there in the library, but we have not loaded the library. So what happens when you randomly, without loading the library, put in some command is, it will throw an error. It will say that there is no item called Biocro on the search list. At the same time, if you load the library, and then you run the same command, let's put here, then you get the results over here. Now, suppose we want to obtain these results, it will be a task to come back to this place and keep looking at what all functions are available. So what we'll do is we will we will convert this into an Excel file or a CSV file in order to go back to it and check if what all are the functions available. So in order to do that, we can do it by assigning a variable to this data frame. Now we are saying that, okay, functions of Biocro. This is one variable, some random variable name that I am assigning this the list of functions to, and I want to convert it into an Excel or CSV file. So an Excel file or a CSV file is usually called a data frame. You have columns and rows, so it is called a data frame. So I want to convert it to a data frame. So I use this command as.data.frame. Now you see inside brackets, it is there's something called base coming. So this base is a basic library that is available in R, and there are a lot of functions that you can use in using the basic libraries in R, which is to convert files to CSV, to write tables, to read tables, to read folders. There are so many commands like this. So one such command is converting the data we need into a data frame. So what I'll do is I'll use this command as data frame. I want this function, this all what is all the functions to be converted to a data frame. So here I will define a variable functions of Biocro and use this command as dot data frame to run this line, this list of functions in package. And when I run this, you can see that under the data in this environment part of in the right side of the screen over this environment part, you can see there is something that has come. Now, when you look at this, you can see how it is formed. There is a column with all of the functions that is written into this data frame. Now, in order to say, okay, now when we are working with this code over here, you can on and off, go back to this function and see what all are the functions available, close it, open it again. But say later on we want to go through what we just want to revise or do something with the list of functions that is available in the package.biocro. What we'll do is we will write this into the folder. We want to save this as a CSV file or an Excel file into the folder. So what we do is we write .csv, right? .csv, which what are we going to write? We'll be writing this functions of biocro, which is basically the list of all the functions. So if you see here, I mean, I told you if you need help with any commands in biocro, you can just type in a question mark and then write in that command, write .csv, and then in the right side they will give you information regarding all that. So here they have said there's write.csv. Inside that you have to write which is the file name that you have. Then you have to there are so many arguments that you can provide. File name, what is the data frame or what is the variable that you want to put in. X is the variable, the object to be written, preferably a matrix. Then file is the character string name, naming a file. So you want this to be written as a file into the folder. So you have to give a file name. Append means it is keep on adding to this file, and there are so many other arguments. Row names means if it is true, you will be giving 1, 2, 3, 4, 5, 6 row names to it. If column names are given true, then 1, 2, 3. If there are a number of columns, then all of the columns will have 1, 2, 3, 4, 5, 6 names in it. So we'll write this file to we'll write this variable into and convert it into a CSV file. Shreyas, if like I said, did you load the library? If you load the library only, you can get this. And before loading the library, you need to install the package. I think I had taken that in the last class. If you want me to do that, you just put in a message in the chat. Yeah, so write CSV over here. The variable that we want to write is functions of biocro. It has already come here. So you just if it is loaded over here, you can see it already coming in the drop down list. Just select it, comma. What is the name of the file you want to? When you save it inside the folder as a CSV file, what is the name of the file that you want to give? Same name we can give, function. It is important that you put it inside double quotes because this is a string. This is a bunch of text, a name that you're giving. So you can write functions of biocro dot CSV and also the extension of the file type. Okay. And then when you run this command, this functions of biocro dot CSV will be saved in here. Now, one mistake that I did is I didn't see. I'm still running this program in users del. When I closed the RStudio and opened it, I didn't set the directory. So that is why this file that I've saved will be going into the documents folder here, not to the biocro folder. So what I'll do is I'll again set the working directory to my required directory, which is this biocro codes, and then again run this. Now, if I go to the biocro directory over here, I can see this function of biocro.csv that is already saved here. And if you open this file, you will see a CSV file with all the names written over here. So this way, you can generate files of what are the list of functions available in biocro. Shreyas, in order to install this, you can go to tools, install packages, and in this packages type biocro and you will see this biocro coming. Click on biocro and install, and after that just do as it is shown over here.
Okay, ma'am.
So this was to list all the functions in biocro to see what all biocro is capable of doing. This was to assign a variable to it so that we can go back over here and check what are all the functions instead of always going into the console. It will be difficult because after a point of time, when you run a number of lines, all of this data will be erased. So you can't retrieve it from this console. So in order to retrieve it, what we'll do is we'll assign a variable to this list, convert it into a data frame or a table or whatever possible format is possible, and then view it over here. Now, suppose if you want to write it as a file, CSV file, you can use this command to write it as a CSV file. Now, the next thing is I had told during the BioPro theoretical explanation that all the plant processes are represented as modules in the package. So photosynthesis is represented by a module. Stomatal conductance is represented by a module. Our FVCB set of equations are represented as a module. From that bunch of equation, we can estimate what are the limited photosynthetic rates and also use it to generate the ACI curves. So now what we want to do is we want to get the information of all the modules that are available in BioPro. So in order to do that, we'll do get underscore all. So by the time you type in get itself, you have this function called get all modules. And then again, double quotes BioPro, and you will run. You see that you get something around 83 modules of different type. We see there FVCB is there. We have one layer soil profile. We have Priestley-Taylor transpiration rate to estimate transpiration using Priestley-Taylor equation, soil evaporation, stomata water stress, canopy, that is to simulate the canopy, water vapor properties from air temperature, module to estimate the water vapor properties from air temperature. All of these modules are available. So again, just similar to what we did earlier, we don't want to go back to the console and keep finding out what it is. So what we'll do is we'll assign a variable to this and convert it into a data frame. All modules of BioCro. You can type in any name, but always type in some name that makes sense to you, because otherwise again you'll get confused. So we are converting this into to a data frame, and then again when we run this, we see we get all modules of BioCro as a list over here. Now this will be available in the environment as long as we are using this program. So this over here is a BioCro related command that we got by checking this package of BioPro. Can you please repeat the fifth step? The fifth line. Okay. So here what I'm doing through this line ls is to list all the functions that is available within this package BioPro. So when I run that line, I get a list of packages, list of functions that is available in BioPro. You see, one such function is to get all the modules of BioPro, get all the solvers of BioPro, get all the quantities that are used in BioPro. Another one is to run the entire BioPro model for the entire crop. To obtain soil parameters, there is one function, and many more. So I want to know what all functions are available in BioPro. I can use this command ls, and in this format, if I put in double quotes and the package name, I'll get all the functions in BioPro. Similarly, say we are using another function, like there is a function called library lattice, which is helping us plot XY plots, scatter plots and all. So we want to know about what are the functions available in this library. The same way, the way we do this, the same way instead of BioCro, we will type in lattice. And then we will run this. We will get the list of functions in this lattice package. So any package that is installed, if you want to explore what all functions are available in that particular package, you can just, this is a general R command. If you put in ls and in this format and put the package name over here, you will get the functions in the package. The important thing is before putting in all this command, you have to load the packages using this command library. Only then you will be able to list all the functions inside the library. Now here also we can see there are some, nothing makes sense, but you can see panel grid. Maybe this is something that helps us to make the plots in the form of a grid. Then there is strip plot, maybe plot strips of bars or something. XY plot is there. This is something we always use, that is to plot scatter plot. So that is what this function does. Now in this line what I did is I don't want to keep coming to the console and looking at what are all the functions. So what I do is I assign a variable to this line, to this command, so that whatever result is being generated when I run this command is saved as a data frame. So I'll put a variable and I want to save whatever result is coming as a result of running this line, which is the same over here. If I run this line, I'm getting this result. Now this result, I want it in the form of a data frame. So in order to do that, as data frame, I want the result of this line, which will be saved in this variable. So when I run this line, I will get a variable over here that has got all the functions in BioCro that I obtained using this by running this command ls for package. And similarly, if I want to save this as a data frame, I will use this command write.csv, and which is the variable that I want to save. Inside this variable, you can find the data frame. So I'll be saving this library, this variable into this file name. And when you run this line, you will, wherever you have set the directory to, you will get that file over here. See, so since I ran it at 325, you can see this file was again modified at 325 to get this function. Okay, so those are some basic things that you that I'm just doing so that you can get an idea. You can explore further on this. These are not functions of BioCro. These are just how to use R in a very simplistic manner, and very briefly about how you can use R. So again, over here also what I'm doing is I want to get all the modules of BioCro. Again, since I don't want to go to the console, I'm assigning a variable to the result of this command. So when I run this, I get all modules of BioCro in the form of a data frame. Now, another thing that I wanted to explore was the using this function, getting the information about a particular module. So here there is a function called module info, which if I run, I will get information regarding a particular module of BioCro. So what I'll do is I'll use this function module underscore BioCro. Now, if you see module underscore BioCro, I'm trying to find out how to, what are the arguments? Whatever you put inside these brackets are called arguments. So what are the arguments this function requires to run successfully without an error? I can understand by doing a question mark module underscore info and going to this right side where it will give the help about this module underscore info. So module underscore info returns essential information about a BioCro module. And what are the things that I need to put here? I have to type in this name of the command, and as argument, I have to give the name of the module. Now in BioCro, whenever you are giving the name of the module, you always have to put BioCro first and then name of the module. So the name of the module is, we got all modules over here. So I want to explore FVCB module because this is what we studied. So what I'll do is I'll take this module name from here and then paste it inside this double quotes so that there's no spelling mistakes or anything. And then when I run this, I get information regarding this module. See, this module's name is FPCB. It has the following input quantities: CI, intercellular carbon dioxide condensation point, the rate of electron transport, Michaelis-Menten constant for carbon dioxide, Michaelis-Menten constant for oxygen, the O2 concentration inside the leaf, a dark respiration rate, the triose phosphate utilization rate, the maximum carboxylation rate, then alpha TPU, that is a parameter usually given as 0 because we don't need that. It is given as 0 usually. Electrons per carboxylation, which is 4.5, and electrons per oxygenation, which is 5.25. See, when we give all of these input, we get the next assimilation, which is a minimum of AC, AJ, and AP. This we don't have to be bothered about. That is for the purpose of this module. And this module is a direct module. You can see there are two types of modules, direct or differential. Direct module is one where you give input, you get output. Differential modules are one which are unsteady modules. That is, you have to differentiate it with respect to time. So such modules are called differential module, and they don't need a fixed step Euler ODE solver, which is called numerical criteria for numerical method that is used for solving these equation in the FECP model. So we got the information about the module. Now again, I don't want this as go here and check it. So I want to read it as module underscore info of FVCB and module info. Now let me try just running this. You will get, since I didn't convert it into a data frame, the kind of file I'm getting here is a list. So I'm getting the module name as FVCB, inputs as CI, G star, whatever, outputs as this. It is a direct type of model, Euler requirement, and error message. Now suppose I want to convert this into a data frame. Let's see what happens. An error comes. It is because for a data frame, you should have uh, a certain number of rows and certain number of columns. But here you see what it is a list with module name. There is one. If this was getting converted into a data frame, inside module name it will be one row. Under inputs there will be like 10 rows. Outputs also has some 10 rows. Type has just one row. So it is a very uneven kind of a matrix. So in such cases, such files cannot be written as a data frame. So in order to do that, we have, if we want it in a particular format, what we do is, now we ran all this. We will not use this as, instead of that, we'll do data dot frame module name is equal to wait, let me just first run this. I'll run this first. Module info of Biocro FVCB. Then I'll go here, module FVCB data frame. This is one variable name that I am putting, and then I want it in the form of a data frame such that the all modules of module info of FVCB dollar module name module underscore name is equal to module info of FVCB. So this file that I ran over here, module info of FVCB, gave me a list, something like this. a list of what are the names of everything, but I want to save it as a data file, or I want to save it as save it in the form of columns and rows. Then using this data frame command, I will give the heading name, module name over here. And under that module name, what I want is module underscore info of FBCB module names. Or say I don't want the name and all. I just need the inputs of that. So inputs is equal to module info of FBCB, and then I put a dollar sign over here and press tab. Whatever are the lists, the name of the headings in the list will come here. So I want inputs to be equal to the inputs in this list. So I will select this and I'll run. What you see here is in the FPCB data frames, I will get the inputs alone. So this way, using this command data.frame, if I want to extract only a particular data from a bunch of data, I can do like this. I can name the column of the heading of the column as input, and then extract data from this variable where the list is stored by putting a dollar sign and selecting out whatever I require. Now say I want the outputs alone. Then I'll run this command, and then I'll get outputs. But see, the heading is input, so it's because I didn't change the heading over here. So if I put outputs here, module info of FPCB, this list dollar, what is the data that I require, and then run this line, I will get a data frame of outputs, and these are the outputs that are being used in this model. So this is how this is again something to extract the data from the modules. Now all these modules are in the form of some random text over there. So if we want to structure it into a particular kind of file that we require, we can do some stuff like this. Now, yeah. Now what I want you to do is, I have a problem over here. In this problem, I have given you need to find the Rubisco limited photosynthetic rate, which is AC. Now for that, I have given the value of VC max. Where is the- Okay, so I've given the value of VC max here, temperature here, what is the oxygen concentration within the leaf, what is the carbon dioxide concentration within the leaf, what is the formula for a Michaelis-Menten constant, what is the formula for oxygen and carbon dioxide, the molar constant value, and what unit the leaf temperature have to be. So what you have to find is you have EC max, you have the value of intercellular carbon dioxide concentration. You need to find Kc, K naught, and carbon dioxide compensation point from this data over here. I've given a table with A and Ci data. You need to find the compensation point from this data, substitute all of that in the equation, and find the value of AC. So you can start doing it now. This might take a bit of a time, so all of you just start doing it, and then as and when you get the answer, just let me know of Kc and K naught. If it is wrong, then I'll stop you there itself and ask you to correct it. So you can put in the chat box what are your answers. Please direct message me. Do not post it to everybody. So, please do this. This will be interesting for you to when I'll be now again taking you to BioCro to see how BioCro estimates it, and then we'll cross verify if your answers are correct or not. So you can start doing this. Anybody has any doubt, please do ask. So carbon dioxide compensation point, it is nothing to calculate. Carbon dioxide compensation point is the intercellular carbon dioxide concentration, intercellular leaf carbon dioxide concentration when the net carbon dioxide uptake will be zero. That time, the respiration rate, the photorespiration rate will be equal to the rate at which carbon dioxide is being taken inside. So totally, the net uptake of carbon dioxide will be zero at that point. So from this ACI table, you just have to find out what the carbon dioxide compensation point will be. There's no calculation or anything to be done. I think all of you might have figured out what the carbon dioxide compensation point is, tau star. So can you put it in the chat box now? Direct message, please don't put it. Yes, Harita, your answer is correct. First, find out what is the value of the Michaelis-Menten constant for carbon dioxide. One important step you need to do is the unit in which leaf temperature is represented in the equation is in Kelvin. So you have to convert whatever temperature data you have to Kelvin first and then substitute. Otherwise, you'll get a very weird answer. Um, Harita, did you convert the temperature of leaf, which is in 28 degrees Celsius, to Kelvin? Okay. Now you need to multiply the smaller constant 0.008314 and then divide 79.43 divided by that answer. Then you will get something around 35 or something, 35 point something. When you subtract 38.05 minus that answer, you will get a particular value. You need to find the exponent of that value. So probably you're doing something wrong in the calculator. First, find out the value of this part, the power part of it, and then finally take the exponent of that answer you're getting. If you put everything together, probably that is why. I hope every one of you are trying it, attempting it. I'm waiting here so that you guys can have time to do it. Has anyone got the Kc value yet? Okay, please drop in a message if you're not doing. If you're doing, I can wait. If you're not doing, just drop in a message directly. I would like to continue. Nobody is attempting. Okay, what is the Kc value you got, Reyes? Is this a final answer, Anamta? So I think we'll go ahead with to the solution. So the Kc value will be 558.76. This is the calculation here. The carbon dioxide compensation point is the intercellular carbon dioxide concentration when net uptake is zero. So the value corresponding to zero over here is 133.41. So 133.41 will be the gamma star value. Then Kc is done like this 0.008314 into 301.15. When you add 273.15, which is the term for converting calcium Celsius to, yeah, so Celsius to Kelvin is C plus 273.15. So when you do 28.28 plus this value, you will get 301.15. And that when you multiply with this value, divide 79.43 divided by this value. And finally, you will get the answer as 558.76 and K naught value as 320.49. This is pretty direct calculations you can do in the calculator. You need a calculator. Now, using all of these values, we will get the AC value as 12.99 by substituting. We know that one VC max is 131, 250 is the CI value, gamma star value is 133.41 divided by again CI is 250, Kc is 558.76, 1 plus oxygen concentration inside the leaf is 210 divided by 320.49 is the K naught value. So finally we will get this answer as 12.99. Now if you want the net photosynthetic rate, I have given the dark respiration rate as 5 micromoles per meter square per second. So when we minus that value also, we get 7.99. It is okay if you find till here also, because I'm just putting this so that I can clarify this confusion that might come when we are estimating using biochrome. So that is the reason why I put this. I also subtracted the dark respiration value from this value. Okay, so this is pretty direct substitution and finding the, I mean, using a calculator to find the answer. Finally, the AC value we get it as 12.99. Now, the same thing, let's try doing it in, um, let me just erase this. Okay, now let's try doing the same thing using BioCro. So I said FVCB model is the model that is used for finding all these carboxylation limit. Before that, does anyone have any doubt regarding this? If there is any mistake, I doubt it's probably a numerical mistake, the calculation errors that you are having. So you can do it calmly later on and see if you're getting the same answer. everything is just direct substitution into that formula. The carbon dioxide compensation point is something that you just need to find from that graph. I mean, from the data that I gave. Rest everything is direct substitution. Does anyone have any doubt other than the calculation errors that might have occurred?
Not yet, ma'am.
Okay. So in that case, let's see how we can get run this FECB module in BioCro and get the answers. So for running a single module in BioCro, what we have to the function that we need to use is evaluate module. So here we are going to evaluate this module called FECB evaluate module, and if you check again, if you go here and check how you need to use this module, you can just put question mark and evaluate module, and you can see in the evaluate module you have to give the name of the module and input quantities. So our module name is BioPro FECB. And the input quantities that we have should be provided in the form of a list. So there are different types of data forms when you use any coding, any program. There are lists, there are data frames, there are vectors. So in BioPro, when you need to provide the input quantities for this module, you have to input it as a list. So how do we know that what kind of a file that we need to provide? Should it be a list? Should it be a vector? Or should it be a data frame? You can see from here the arguments. It is a string specifying one particular module, formatted like the library name, which is BioCro, and the module name. Then input quantities, a list of named numerical elements, not only values, but you have to name the values also. So we know that our input names over here are, uh, let me get the input names over here first. So first I want to know inputs of FVCB data frame, inputs is equal to module info of FVCB inputs. So here if I go to inputs of FVCB, I need all of these inputs. So CI, G star, J, KC, K0, OI, all of these. So what I do is I take all of these from here, go here. In this evaluate module, the input quantities should be in the form of a list. So first I'll write list, and then inside the bracket, I will put in all the list. Now you see, this has two, let's remove all of this. Now CI, we need to give a value. So the CI value that we had given in the question over here is 250. So here also we will give 250. After that, we'll put a comma, and then we'll give the G star value. G star value or tau star, the carbon dioxide compensation point was 133.41, comma. Let's remove this. We don't need this. This is not an input. J value, we didn't give anything. This is for calculating the RUBP regeneration. We are not doing any carboxylation for the carboxylation limiting calculation. You don't need J value. So irrespective of it, let's put some J value, 200. Then comma. Next is KC value. KC value, we got it as 588 point, is it 588.76. So 588.76, comma, K naught value as 320 point something, 320.49. So I'll put in that value. Then oxygen concentration inside leaf is 210. I put that value. Then RD value is 5. Okay. TPU rate, let's put some value again, not required when we have to calculate the carboxylation point. VC max was 131, comma. Alpha TPU is something related to again TPU rate concentration. We'll put that as 0. That needs to be put as 0, comma. Then electrons per carboxylation will be equal to 4.5, comma. And electrons per oxygenation will be equal to 5.25. So that's it. Now you have to see this comma. All of these values are coming within a list, and this list's bracket starts here. So you have to close that bracket. Again here you will see this bracket has also need to be closed. So that closing bracket should also be provided at the end. Now, when you evaluate this models, hopefully we will get some answer. Bingo, we got the answer. See, the AC value is equal to 7.47, AJ is 4.23, AN is 4.23, AP is 25, VC this much, this much, this much. So we got the AC value 7.47. We were getting it as 12.99 over here. 12.99 minus 5 is 7.99. Relatively closer. Let me just check what. Is there any other value that is a bit different from our PPT? 131 to 558.76. I gave 588. That is why the difference. So now when you run this line, you see that you get 7.99. This is the same answer that we got here also, 7.99. So this is how the model will estimate it for us. We can evaluate this particular model by using this command line and giving the input quantities as a list. It will give us all the values. What is the value of the AC, that is the maximum carboxylation limited photosynthetic rate, maximum electron transport limited or Rubisco regeneration limited photosynthetic rate, what is the TPU limited photosynthetic rate, what is the net photosynthetic rate. So the minimum of all these three quantities has been taken as the net photosynthetic rate, which is for the AG synthesis. Hello, am I audible? Okay, I hope I'm audible.
Yes, ma'am, you are audible.
Okay. So that is how you run a particular module, how we ran the FVCB module over here. Now, next what we want to do is, we want to create ACI curves from this FVCB module. For that, the command that we can use to create curves, ACI curves from this FVCB module is module response curve. So again, we'll check how does what are the arguments that you need to give for module response curve. So you can do module question mark module underscore response curve, enter, and you'll see the right side over here. You have to give the module name, not just input quantities. You have to give the fixed quantities as well as the varying quantities. So let's now use the module response curve over here. So I'm going to generate ACI curves using the module response curve. And I need the name of the module that I'll be using for generating the ACI curve, which is our FVCB model. So that module name I'll write. Now I need fixed quantities. So in ACI curve, the values that are going to change are the concentration of the intercellular carbon dioxide. So remaining all of this will be a constant except for this quantity which is going to vary. So what I'll do is I will name a variable that gives us fixed quantities, and it is all of these. List of all these input quantities that we have. Okay, except for Ci. So Ci we'll remove from here. Okay. Now varying quantities will be Ci because the x-axis is what is going to vary, and what we want to generate is the net assimilation rate. We don't know the net assimilation rate. The output of this FECB module is the assimilation rates, all the limited rates. So varying quantities, I want the assimilation rates for so I want it for CI values starting from 50, ending till 1800, and having an interval of 100. So in order to give a sequence of values, we can either give it as one by one value, 50, 100, 120, 130. That particular values will have all the net assimilation rates generated. But here I want to give it in a sequence. This is much more easier to give. So sequence is one command where it will start with 50, end with 1800, and it has to have an interval of 100 micromoles per mole concentration between each value. So this will be the varying quantities. Now I've got the fixed quantities and the varying quantities. The fixed quantities is equal to this fixed quantities variable that I have defined. Run it. Okay, you have to be careful to run both of that. It's showing an error over here. Electrons per carboxylation, electrons per oxygenation. Okay, this bracket is not necessary, so that is why I threw an error. Yeah, now it is working. Varying quantities I run. Fixed quantities is equal to this fixed quantities that I just obtained. Fixed quantities, comma, varying quantities is equal to the varying quantities that I just ran. Now, if you run this command, you will get the module response curve. And if you see the module response curve, where is module response curve? No, we named it ACI curves. You can see over here. For each value of CI, the answer AC value you get, AJ value you get, AN value you get, AP value you get. All these values you get for this particular value of CI. Then for 150, we are getting these values of AC, AJ, AN, and AP. So these are the values. You get a data frame of calculated entities. For each value of CI, they use this equation and find the AC value. They use the RUVP regeneration limited equation to find AJ value, and 3 into TPU rate to find the AP value. They find the minimum of all these three quantities and find out the AN value. So that for each value of CI, they are doing it because CI value is the only value that is varying over here. They find it for each varying value of CI. Now we want to view this as a graph. I mean, ACI curves, we have viewed it as a graph. So for that, we will be using this library lattice to plot this graph. And in order to plot this graph, what I'll do is I'll use the command xy plot. And in the y-axis, we want the value of AC. The data is going to be ACI curves dollar. I want in the y-axis all these values AC plus ACI curves dollar. I want AJ AJ value plus ACI curves, AP value, and let's see, you put a tilde, and in the y-axis we want the CI values. That is how ACI curve is. Sorry, y-axis we want the photosynthetic rates, x-axis we want the CI rates. When you plot this, you get a graph like this. In the right hand side, you can see one graph over here. This has got the AC values, AJ values, and AP graph. You can see now we don't know which color is what and all. And we need a line graph. So I put type is equal to line, L for line, and we get a line graph. Now, if you see, again, we don't know which curve is representing which photosynthetic rate. So there is something called auto key, which will give us the a legend. So I'll put auto key is equal to true, and here I will get AC curve is the one in blue line. This line is AC curve. J curve is the one in brown, and AP curve is the one in green. So AP curve is a straight line. And then if we want the A net, we can know from this all the three ACI curves that the A net will be the minimum of all the three values. So A net will be something, and you have to be careful. The minimum value will be taken from zero value. The bottom values, the photorespiration values will not be considered for taking the minimum AC. So minimum values, this brown curve up till here, it will be the brown curve. And after that, the TPU limited curve will be what? Contributing to the ACI curve. So if you want to check how the net is working, then again I put AN also over here. And then from that you will be able to see this AN curve is by this red line. This red line is covering this AJ curve, and then when you come here, the minimum value is of TPU rate. So that curve is what is being highlighted. So this is how you will create the plot using XY plot. Now we created this very robust plot. Now I want to create a plot that is a little more beautiful, that is a little more understandable. So what I do is, in the same XY plot itself, I will make a plot with AN. So for AN, I will do, this is what XY plot. The data that I'm using over here is ACI curves. You can see it is ACI curves. And in the y-axis, I want AC, AJ, AP, and AN. And the x-axis CI. And I want both points and line as well. All this you can put, all the aesthetics you can put it within this XY plot. For type, I want, initially I had put only line over here, but now I want both line and point. So I will put this as a vector over here. Put C bracket point, P for point, L for line. I want the point size to be 16. I want the colors of this first AC to be red, AJ to be blue, AP to be green, and AN to be purple. The width of the line should be 2. The x-axis should be intercellular carbon dioxide concentration. Y-axis should be photosynthetic rate, and auto key true for the legend. I will run this, and you will see. This is not coming with AN not formed. Okay, the S is not there, so that is why it is throwing an error. So I'll run this now, and when I plot it, see I got a beautiful graph over here. In this beautiful graph, I can see AC, which is blue color, is no longer the lesser number. So that is why this part is actually lower value. So that is why it is being covered by the purple value, which is forming the AN value. AP is green, AJ is the carboxylation, sorry, the RUBP regeneration rate. Now I want to compare what this, I don't want this purple line. I want to just compare which parts of the curves are contributing to the final A net. So for that, I'll make another plot with AC, AG, and AP alone. And remaining everything is the same except that AN will not be there. So again, I will run this. And when I run, we can see the three different values separately over here. The red color is for AJ, the green color is for AP, and the blue color is for AC, which is Rubisco Limited, TPU Limited, and RUBP Regeneration Limited curves. But with the AN value, this part of the curve will be the net contributing to the net photosynthetic rate. Now, what I want to do is I want to combine both of these plots to compare how, which are the lines that are contributing to the net photosynthesis. So I make use of a library called cowplot, which helps in uh, generating combined plots. So in that, there is one command called plot grid. If you say plot.grid, you see here. You can see it is coming in inside this cowplot library. There is something called plot grid, and then you have to provide whatever what are the plots that you want as in the form of a grid. I want with AN and without AN. And then when I enter, I got a plot. You can zoom this over here to show that this plot is with the AN curve and this plot does not have the AN curve. So I can compare which parts of the photosynthetic rates are contributing to this net photosynthetic rate. So you can see here the blue line until this point, it is a blue line. Then after that, it is the green line. Use the pen. So you can see here this blue line is what is okay, it doesn't work. Annotate. From here onwards, it is a blue line. After this point, it is a green line that is contributing to the net photosynthesis. Here also you will see that it is a blue line that is covered by that purple line. And then when it comes here, it is a green line that is covered by the purple line. That is the net photosynthetic, the ACI curve for the net photosynthetic rate. So this is how we make use of this model to now is this thing you can even save it. You can export this as an image or a PDF or copy it to a clipboard and you can use it in documents. Right now I'm not doing anything. Okay, so this is how we make use of this BioCro program with all the equations. So we know there are three equations and all those three equations have been built into this particular module FBCB so that we can run this particular module and obtain uh, the results of all the carboxylation limited rate, oxygenation, RUBP regeneration limited rate and TPU limited rate. And not only can we do that, we can also plot such graphs, generate such ACI graphs wherever required for a better understanding, and not just generating graphs. When we assign variables to these, we get the entire data. See, this is the formula. We get the data of what are the numbers that are coming within this. Here the ACI curves, we get all the values over here. So if you want to use this data frame in Excel or somewhere, you can do the same thing. If you're not very familiar with R for regenerating the data or regenerating the graphs, you can make use of this data in Excel also. Now, if you notice here, we had used this CI value is equal to 250. So CI value is equal to 250. We had found out that AC value is 7.9981. And here also, if you see, for 250, it is 7.9981, which is exactly the same value that we obtained from our calculation. And if you go back to this data, I had made use of this data for all this BC max. Even here, if you see, the it's coming around 12.488, the net photosynthesis. This is a measured data that I had measured using Leica instrument. And in that data, at this level of intercellular carbon dioxide, the whatever value we got only, we are getting here also, somewhere near to that. So that means the VC max value and all these value corresponding to this data is similar to the measurements that we had made. So this is how we make use of this models to replicate these complex plant processes. All of it, whether plant or any other processes, are bunch of equations that can be written in using a particular programming language, and then it can be run using programming languages to obtain the result of such complex processes. So that this is where plant modeling has its advantages. When if you sit to do it manually, it's a highly time consuming process. But instead, by using this model and the code, we can generate results in very short time. So in the next class also, yeah, I think that will be the end for today's class. Demonstration of how to use the FECB module in BioCro and certain functions within BioCro that will help you to get all the quantities and everything. So I'll be posting this the code, whatever we did today. I'll be posting the R code. You just have to run it uh, and see for yourself what are the results. Um, I understand it might be a little bit overwhelming, the coding part, the running the code, but you can eventually go through the code again and again. If you have any doubt, you can post it in the Google form that I send you, that I've posted in the WhatsApp group, and clarify your doubts in the coming sessions or as per your convenience. So this will be for today. If there are any doubts, I can clear it. Otherwise, we'll be ending today's session. Thank you for attending today's class.